The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for joining us today for our webinar with our speaker, Darren Scott with Carus. I'm Ashley Swingle, Marketing Specialist, also with Carus. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut down on any background noise. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. If you're interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. Do you receive our email blasts for upcoming webinars, presentations, trade shows, and technical information on our various solutions? If not, sign up on our website. You can find the Join Our Email list on any landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And we can't forget to mention our social media platforms. We encourage you to connect with our Carus page as well as our team members on LinkedIn, where we often share upcoming events, including webinars, industry articles or news, sharing relevant posts from industry experts, and more. Listed here is our website link and where you can find a list of upcoming webinars. And at this time, I would like to take the opportunity to introduce our speaker, Mr. Darren Scott. Darren has worked for Carus for over 20 years, and as the technical marketing specialist, he conducts laboratory testing and product demonstrations for Carus's municipal, industrial, and environmental customers and prospective new customers. These product demonstrations include technical training, safety presentation, and installation of safe chemical handling and dosing systems. He is a graduate of Illinois Wesleyan University in Bloomington, Illinois, with a Bachelor of Science degree in Chemistry, ACS certified. Mr. Scott is a member of the AWWA Water Environment Federation and the American Chemical Society.
Thank you, Ashley. So our agenda today for this presentation is we're going to cover what the problem is at the wastewater plant for total phosphorus, the solution to that problem in the ultra-low nutrient removal, some plant trial data, conclusions, and then like she had mentioned, any questions you may have, put in the question pane and we'll answer them at the end. So what is the phosphorus problem? So there's a lot of regulatory pressure on phosphorus effluent discharges from wastewater treatment facilities. The goal behind them is we know that the discharge of phosphorus to rivers and streams can lead to algae blooms out there in the environment. So one of the ways that many states and the EPA is trying to limit the amount of phosphorus is to tighten those limits at the wastewater treatment facility and lowering that dosage. Initially, most plants have dosages of about a discharge limit of 1 milligram per liter as total phosphorus that they have to discharge. If that limit goes lower to 0.3 or to 0.1 or even lower, then they have to try different treatment goals to get there. In the case of ultra-low nutrient removal with our product versus alum or iron salts, you can see that there's an increase in the amount of chemical dose as you have to get to lower and lower dosage limits. So you'd have to increase the dosage of those other products in order to meet the lower target goals for total phosphorus. Like I said before, initially what all these effluent limits are driven by is what the body of water the wastewater plant is discharging their phosphorus into. As you can see in the picture, a giant algae bloom on a lake. And one of the things is that can impact the drinking water plant downstream from your wastewater plant in many different ways. It can cause taste and odor issues for the drinking water plant. It can cause increased loading to the drinking water plant where they have to add more coagulant to remove that algae. And depending on the type of algae and what time of year it is, they can also release cyanotoxins into the water, which have a health limit as well. So that can affect the drinking water plants greatly. So one of the ways to eliminate algae from these rivers and streams is to lower the total phosphorus being discharged into them. Typically, we see a lot of these increase in these permits in the Midwest, on the East Coast, and some of it a little bit out west for trying to remove this total phosphorus from the discharge. Most plants already have some type of treatment in their plant to remove total phosphorus prior to their discharge to the river or stream. Some of the most incumbent solutions that you see out there for municipalities are the three products listed here: aluminum sulfate, polyaluminum chloride, and ferric chloride. They each have their own individual pros and cons. In the case of aluminum sulfate, it's pretty inexpensive, it's very widely available, and it's pretty easy to use and apply. Now, there are some drawbacks to using aluminum sulfate. It's best within a very targeted pH range. Otherwise, you might have to feed more in order to get to the lower total phosphorus levels. Dewatering can sometimes be difficult because the sludge will become gelatinous from the increased dosage of the aluminum sulfate. It does generate quite a bit of sludge when you use it. It doesn't always work the best to get low turbidity removal in your plant, which means it also can increase your settling rate, so it may take longer for the solids to settle in your clarifiers. It does have a freezing point down to 9 degrees Fahrenheit, but you can get some crystallization in the feed lines, which means you might have to heat trace the tank and the lines if you're feeding it outside. In the case of polyaluminum chloride, it is pretty widely available. It does create less sludge compared to the alum at the same dosage, and it does work over a broader pH range than alum. It does have a slightly higher cost than aluminum sulfate. It still does have the same slow settling rates that you would see in aluminum sulfate. In colder wastewater, it doesn't help as much with turbidity removal, but it does have a slightly lower freezing point at -4 degrees Fahrenheit. In the case of ferric chloride, pretty inexpensive, pretty widely available across the US. Some of the cons for ferric chloride: it is considered pretty corrosive. It does cause a lot of staining on the tanks and the feed lines of an orange color. If you're feeding ferric chloride and there's the presence of the iron in the wastewater and you have UV disinfection, it can stain that equipment or foul those UV light bulbs, so you have to clean them more often. It does generate quite a bit of sludge, and the freezing point is slightly higher at 14 degrees Fahrenheit. So you can see these are kind of some of the current options that plants are using to remove total phosphorus from their discharge. So one of the challenges that a lot of plants have as their total phosphorus permit level is being lowered is that they're not as efficient when you get to the much lower total phosphorus removal limits. Typically, we talk about a molar ratio, or how much of the product you need to feed per part removal of total phosphorus that you have in the wastewater. At a level where you have a target dosage of 1 milligram per liter as total phosphorus in your discharge, that ratio tends to be about 1:1 for those products, and along with the ULNR. As you restrict that level and that total phosphorus drops to 0.3 to 0.1, or even to as low as 0.075, that ratio starts to climb for the alum and aluminum products to the point where it becomes 3:1, 4:1, 5:1, or even more in order to get to those low levels. At that point, you're going to have to feed much more of the iron and aluminum-based products, which means you're going to generate a lot more solids, which then are going to increase the solids loading through your treatment process, and the solids that you'll have to get rid of at the end of the treatment process. Sometimes, even with adding additional alum and iron salts, you can't get to the 0.1 or the 0.07 milligram per liter lower levels that you need to achieve if that's what your permit's going to go to. The ULNR product is a water-soluble rare earth chloride for rapid precipitation of the total phosphorus in your plant. Because of its high concentration and its formulation, it greatly reduces the amount of product that you need to achieve those ultra-low final phosphorus discharge limits at your plant. Based on that lower dosing, that then ties into less chemical sludge that's generated in the treatment process. The product does not cause staining or discolor facility equipment or structures. It also has a really low freeze point at -37 degrees Fahrenheit. And it quickly forms phosphorus solids that precipitate out and settle very rapidly, both in the plant and in jar testing. One of the ways to determine how much product you're going to feed is you can compare different types of jar tests. What you can see here is some East Coast jar tests where we compared the ULNR product versus polyaluminum chloride. And you can see the total phosphorus concentration starting up around 4.5 to 5 milligrams per liter is total phosphorus. And that molar ratio, that first 1-to-1 molar ratio, drops dramatically with both products. But the ULNR, which is the blue line, drops much quicker to a lower level. Then as you go down, you can see that it takes more and more increasing with the polyaluminum chloride to get to that lower level. At this plant where we were doing this jar test, based on the current polyaluminum chloride dosage treatment, they would need about 225 milligrams per liter of polyaluminum chloride to get from approximately 5 milligrams per liter of total phosphorus down to about 0.34 milligrams per liter as total phosphorus on the discharge. You only needed about 45 milligrams per liter of ULNR to get the same total phosphorus removal in the jar test. So you can see there's a much greater difference in dosage when you have to get to that 0.3 limit. So let's talk about some field trials out there in the Midwest. Our first plant trial was at a 50,000 gallon per day Midwestern plant. In addition to normal wastewater from homeowners, they also had 2 cheese plants in the distribution system that added phosphorus as an industrial input. Excuse me. Their total phosphorus discharge effluent limit of 6 milligrams per liter was going to be lowered by the state regulatory agency to 0.075 milligrams per liter in late 2019. You can see their plant set up in the diagram in Figure 2. Where we decided to apply the ULNR was after the aeration basin, just prior to the final clarifier. In this plant, wastewater came into the process, went to the primary clarifier. Wastewater from the primary clarifier traveled to the RBC units, from there to the aeration basins, and from there we dosed the ULNR just prior to the final clarifier, and out of the final clarifier was the final effluent to the river discharge. Prior to doing the plant trial, we did some jar tests looking at how much ULNR would be required to remove the total phosphorus in the plant. At the time that we did the jar test, their influent level was up around about 6.5 milligrams per liter as total phosphorus. And you can see as you get close to that molar ratio of 1-to-1, we could get down to just about 1 milligram per liter, and then we would have to increase the dose higher to drive it to about 2-to-1 to get to that much lower level. What that would look like dosage-wise was we'd have to be down around 250 milligrams per liter as the ULNR. So that translated to the plant trial. We dosed 13 gallons per day of ULNR into the wastewater. And we also changed. Prior to this application, they had been applying their current product to the front of both aeration basins, and they had 2. Because we were moving it back to the process, we could treat the 2 aeration basins effluents combined, so we only had 1 application point. So it also minimized the feed system that they needed to have as well. On the graph on the left-hand side, you can see the data for the effluent levels and the influent levels. You can see we had quite a bit of variation in the total phosphorus coming in the influent. We had it as low as just below 2 milligrams per liter and as high as 5 milligrams per liter during the trial. Throughout the trial at this 13 gallon per day dosage, we were able to consistently get the effluent below 0.075 milligrams per liter throughout the month-long trial. So meeting their target dosage that they had to achieve. Our second plant trial was 135,000 gallons per day activated sludge facility. They got an additional 40,000 gallons per day of wastewater and sludge from private systems in the surrounding area. Their current treatment process was getting their discharge down to around 4 milligrams per liter, and they anticipated that they were going to get a future limit from the state was going to be anticipated to be 0.12 milligrams per liter from the 4 that they were at now. Same thing here. We ran jar tests at the beginning to see what we could do to get to their new dosage. And the jar test determined somewhere between 7 and 28 gallons per day of ULNR was predicted to meet the discharge permit of 0.03 for the total phosphorus target. For this field trial, the tote was stored outside with the metering pump directly on top of it as a temporary feed system. The feed line was run up the drain pipe and over to keep it out of the way so that the operators could still cut the grass and maintain the grounds while we were running the trial. The feed line then ran over to the discharge point, was tied into a line to keep it suspended below the surface. So you can see that in the pictures here. So we initially started at the lower dosage that was predicted of 8.5 gallons per day. And we initially had started at that lowest dosage of 6.8, roughly 7 gallons per day. Now, I mentioned they had outside private wastewater and sludge that came into the plant, and they would discharge that occasionally into the system as well at the front of the plant. So you can see when we started the trial, about a day into it, they emptied the 40,000 gallon waste holding tank into the system as well. Our total phosphorus concentration dropped in the system, and you can see that we were able to get at 6.8, we could get it down to around 0.25. We then increased the dosage to about 8.5, and it dropped further to about 0.13 for their dosage. So below the 0.3 target that they needed to achieve. Our third plant trial was a plant that was a 25,000 gallon per day activated sludge facility. They did accept some sludge, about 6,000 gallons per day of wastewater and sludge from private septic systems. Their current total phosphorus limit was 6 milligrams per liter, and they also had a cheese manufacturing facility nearby that dumped into their system. And they estimated that their future limit was going to be 0.12 milligrams per liter. Once again, we did a jar test to look at the dosage required. And we predicted somewhere between 5 and 10 gallons per day of the ULNR product was going to be needed to achieve the 0.12 target total phosphorus discharge permit. And you can see that in the graph there as we get lower where the dosage needs to be. Just like the other plant, the setup was a tote outside the building for our application point. We ran the feed line into the building and fed with a small Stenner point feed pump. And then you can see the application point running through the PVC pipe alongside of it with the flexible tubing, and then discharging where we were discharging into the discharge, where you can see there's quite a bit of turbulence. So we got very good mixing at this application point. When we started this trial, the total phosphorus coming into the plant was up around 5 milligrams per liter. We started at about 9 gallons per day of ULNR. We quickly saw a drop in the total phosphorus down to below the 0.12 milligram per liter, which was the target. And toward the end of the trial, we even got a non-detect on the total phosphorus in their discharge. So basically a zero discharging it. at 9 gallons per day. Our fourth plant trial was a conventional activated sludge plant. They had 2 sanitary package plants with a design flow of 0.255 mgd and a peak flow of just about double that at 0.536 mgd. Once again, we ran jar tests to support the plant trial at this plant. Based on a target total phosphorus discharge limit of 0.1 ppm or milligrams per liter, it was going to take somewhere between 6 and 22 gallons per day of ULNR that was predicted based on the jar test. Because they had 2 systems, we set up a tote between the 2 systems with 2 separate feed pumps on top of the tote and ran temporary feed lines into each of the application points so that we could control the dosage to both feed points independently. One of the things the plant had talked to us about was with these 2 separate systems is they didn't always operate the same and they didn't always get the same total phosphorus on the discharge from both sides. So the ability of having 2 pumps allowed us, if we needed to adjust the dosage on one side higher than the other, the 2 feed pumps would allow us to do that for the long-term trial. The influent coming into the plant averaged somewhere between 2 1/4 down to about 1 1/2 during the trial. We dosed 7 gallons per day of the ULNR, and we adjusted the dosage up and down during the trial. So initially, when we started at 3 gallons per day to each side, which was 6 gallons per day total, we noticed that the level dropped, but it seemed to come up a little bit. On clarifier 2, which is on the gray side, and clarifier 1 had dropped lower. We adjusted the dosage up on both sides to 3 1/2, and slowly over time they both equalized and got closer to the dosage of 0.12 milligrams per liter of total phosphorus on the discharge. We increased the dosage at the end of the trial to 4 gallons per day at both sides just to see where the final dosage would be. And you can see they're right on top of each other as we increase the dosage. They were able to, during this trial, to meet their target of 0.12 as total phosphorus on their discharge. In addition to the field trials in the Midwest, we also had a field trial in New England. This plant is a 350,000 gallon per day plant. They have a seasonal limit on their total phosphorus discharge from April 1st to October 31st. In the future, their limit is going to actually be lowered in April of 2022 to 0.1 milligram per liter on their limit. Their current technology that they were feeding at this plant was polyaluminum chloride at 50 gallons per day. You can see an overview of the plant there. You've got the final clarifier. You've got their aeration basins that you can see on the left-hand side of the screen, and then the chemical feed building that we could use in the future with the gray building on the left-hand corner. Once again, conducted jar tests in support of the plant trial to determine what our dosage would be. We looked at the jar test at both the ULNR product that we were going to test and their current polyaluminum chloride product that they were using, and we targeted that current limit that they had of 0.8 and also wanted to see if we could achieve what their future target was going to be as well. What we saw, the initial dosages in the jar test said we were going to have to use about 34 gallons per day of polyaluminum chloride, and the ULNR at the time of the jar test said we would have to use about 23 gallons per day. One of the other things that we looked at in the jar test was what was the turbidity after we had done the treatment. You can see in the picture below, the polyaluminum chloride jars have kind of a haze to them, so they had a much higher turbidity at 52 NTU. The jars with the ULNR, the NTU was about 2.7 in those jars, so a lower turbidity as well. The setup, we used a tote outside next to the chemical feed building. Ran the feed line with flexible tubing to the application point that you can see in the grate, and it was protected with insulation based on the chance for cold weather. During the plant trial, the total phosphorus on the effluent varied anywhere from 2.8 up to about 4.4. And we were able to achieve the target dosage of 0.8 milligrams per liter as total phosphorus with about 15 to 17 gallons per day of the ULNR product. One of the things we also did at this field trial was, besides just the jar test, we used a dosing calculator to predict, based on all the previous jar test data and field trial data that we had, to estimate what our dosage would be for our target ULNR dosage in the plant. One of the things that we also looked at was, in the future in the jar test, we know their upcoming limit was in 2022 was going to be 0.1 milligrams per liter. And the estimated dosage for polyaluminum chloride was going to go up to 61 gallons per day at that point in time. And for the ULNR, we were only going to need 27 gallons per day to achieve that lower limit from 0.8 down to 0.1 in this system. So they had a product that they know they could try in the future to get to that lower limit of 0.1 milligrams per liter of total phosphorus. So in conclusion, the rare earth chloride ULNR product is a very high performance formulation, and it greatly reduces the amount of product needed to achieve the total phosphorus limits at your wastewater plant. Based on these lower dosing requirements, where you feed less gallons per day of the product, you're going to generate less chemical sludge in your treatment process. In addition to the product generating less sludge, it does not stain or discolor your facility equipment or structures, so you don't have to worry about that. It does not freeze until below minus 37 degrees Fahrenheit, so you might not need to put any kind of heat tracing or heating elements around your system if you're going to feed the product. We very quickly form solids that precipitate out, taking the total phosphorus with them, and those solids settle rapidly both in the jars and in the plant, which can help with turbidity issues. The ULNR product can be used to complement an existing system. So one of the things that we talk to customers about is, if you already have a treatment process in place that achieves your current limit, you may just need a boost to get to the newer lower limit. So the ULNR can be used to complement existing systems like disc filters, ballasted sand, or biological removal. If those processes can get you to a lower dosage of, say, 0.5 or 0.3 milligrams per liter, but they can't get you all the way down to a limit that's 0.1, you can then add the ULNR at the back of the process as a supplement to those systems and get that last 0.2, 0.3 of a part out of your system to get in compliance with your new future permit. One of the things at Carus, we want to help you solve your phosphorus discharge limits. So please give us a call, and we can walk through both a jar test, a calculated dosage, and then help you with a plant trial to determine what dosage will achieve your total phosphorus permit levels at your treatment plant. We do know at Carus that every system is unique and every system is slightly different. So it's good to have that discussion going into it of what obstacles we can overcome and how we can help you meet your compliance goals.
Thank you, Darren. At this time, we will start taking questions, and while we wait for a few to come in, I'll go ahead and go over the current slide. It shows our sales managers along with their contact info. Feel free to reach out to yours in your region. And it looks like we do have a few questions that came in, Darren.
Okay.
The first questions, was there ever a dosage that was no longer effective in removing total phosphorus?
No. So in all the field trials that we've conducted in the last year, we've never seen where it hasn't been able to get us to the dosage that we need to get to at the plant, both for their current permit and for their future permit where we've tried it.
How would it work in a lagoon system?
So one of the things we think with the lagoon system, and we have not had a plant trial at a lagoon system, is you'd have to be able to apply it to the lagoon, so either to the influent to the lagoon, so that way you get good contact, or apply it some other way to the lagoon so you get good contact. The one thing we do at most of these treatment plant systems that are different than lagoon, we usually have a concentrated discharge point that we can apply it to, get very good mixing, and then we go to a final clarifier before it gets discharged. In the case of a lagoon, we'd probably want to treat the influent going into the lagoon, get that precipitation to happen in the lagoon, and then you'd be at the lower level on your discharge. But definitely contact us if you have a lagoon. It's something we would like to work with you on.
Is the jar test something you do for free?
Yes. So the jar test and coming on plant site to do that is something we can do for free. We've done both sending the wastewater into our treatment plant, which obviously is probably something we might do a little more often considering the current conditions out there. But we've also in the past gone to the treatment plant. What that allows us to do is walk your treatment system, talk to you about where your application points are, what kind of wastewater equipment do you have. That allows us to pick the best application point, allows us to pick where we would put feed equipment, and then also run the jar test so you can see the product working in the jars and what the levels will be. So that's definitely something that we'll do free of charge.
Thank you. And do the products consume alkalinity?
Yes. So all the chemical coagulants will consume a little bit of alkalinity, and it's going to be based on dosage. So the aluminum and iron-based products, because your dosage will be much higher, will consume more alkalinity than the ULNR product. Because we're at a lower dosage, we don't need as much alkalinity to get our precipitate to form.
Some of the case study graphical data results indicated a target total phosphorus value, but the phosphorus testing results were shown as orthophosphates. Can you clarify if the conversion factor was included or not?
So yeah, so one of the things I didn't mention in some of the plant trials is we collected data on the plant site and we wanted immediate feedback rather than sending the samples out to a certified lab, which also was part of the follow-up that we did. So on the plant site, we ran just an orthophosphorus test and just did that conversion. So it was total orthophosphorus as a dosage. And if we saw the drop off in that level and it got close to our limit, we knew when we sent the sample out for total phosphorus testing with the digestion that we'd be very close to our dosage. It's one of the things that also has come up. In wastewater, we always refer to everything as phosphorus, as P. So we're very clear that when we do that testing, that we're always measuring phosphorus as P. And then if we're doing orthophosphorus or total phosphorus, we reference that in the graph. But the reason some of those graphs, they're showing the orthophosphorus testing that we did on site, which we did more frequently than the outside testing where we did the total phosphorus. And that was just to give us an idea of where we were at.
Okay, and how might this be used for biosolids?
So it's not really used currently in biosolids. So we're always treating the wastewater prior to it being discharged. As the ULNR reacts, it forms phosphorus solids that precipitate out. Those solids will end up in the biosolids itself. So as we generate solids, they'll end up in the wastewater, biosolids, and then you'll do your standard dewatering process. One thing that you may notice in your plant, if you're having issues with struvite formation in your biosolids process, struvite forms with phosphorus and some other components in your wastewater system. If you were feeding upstream of that process where you had your dewatering, so you had your centrifuge or your belt press, and you were getting struvite in that system, if you remove the phosphorus upstream with the ULNR, there's no phosphorus there to form the struvite, so then you wouldn't see it in those other processes downstream. Generally, we're farther back in the process, so we won't impact that, but it's something that you can consider if you're having issues with struvite formation early in the process. You could then add it prior to like the aeration basins or farther up in the process to prevent that forming in your plant.
And it seems that low flow rate performs better. Why is that?
Not sure exactly what that question is. The dosage is, typically we've ended up around 1-to-1 on the molar ratio, regardless of what the flow rate going into the plant is. But that's something, if you want to send us a question offline and with a little more detail, we can probably answer it there.
Okay, and does this interact with sulfide the way that iron salts can?
No, so iron salts will precipitate out hydrogen sulfide. This will not do that.
What is the current price cost per pound or per gallons?
Please reach out to your regional sales rep to have that discussion, because it'll depend on how much product you're buying and your package size.
Do we have any pilots on any larger plants, like 8 MGD or 30 MGD?
We do not at this time.
And last question, it looks like, what is pH of wastewater impact?
So the addition of the ULNR, because of our low dosing, we haven't seen an impact to it lowering the wastewater pH after application point. So.
Okay, and I think that's it for the questions. Thank you, Darren, and thank you everyone for tuning in. Have a great day.